Hold on just a second, okay? Okay, so now let's do some review, okay? So if you look at the homework sheets, some those circled with red circle, so these are the problems you may want to pay attention. But it doesn't mean that the quiz will just cover these kind of problems, so cover a little bit more. And actually, I'm going to indicate that during the review. So the first two problems, so I'm going to go through this in this order, okay? The first two problems are similar. I mean, basically they are testing your understanding about open set, the concept regarding open and closed sets, okay? So for instance, so I'm not going to go into details, and you can look at by yourself. For actually, there's a two-way to handle that. One is local way. That means you argue individual point to see whether the point is interior point or not, right? But there's also global way. Global way is you use the global open closed set properties. Like for the first problem, you want to look at the different set, G minus F. Now you can express this G minus F in terms of G intersect with R minus F. Now we are giving that F is a closed set, so therefore the complement of F is open. So if you look at right side is basically two open sets. Therefore the intersection is open. So this will immediately give you the result. So as long as you can formulate things like this, you can use the global open set or closed set property to prove it in a very short, very quick way, okay? Now the same thing happened to the second problem. You can argue using pointwise argument, or you can turn this into using similar argument. You can turn F minus G into F intersect with the complement of G. And then you can see the right side will become the closed set, the intersection of closed set. And of course, it is also closed, right? So also give you a result. So in the in the quiz, there will be a problem like this, similar, but maybe a little bit more complicated. For instance, here you have just one hole. So you have a F is a closed set, and there's a hole, open hole G. Maybe you have two or more holes involved. Then you can do the same thing, right? Prove the same result. And so once the holes are removed, and these are just the remaining part will be a closed set. So as long as you can establish set identity like this, you can use the same argument. Okay, so this is 1 and 2. One just a second. These are chat. Yeah, this lecture will be recorded, of course. Thank you for the reminder. Okay, all right, so let's continue on. So the second one, there's a sequence. So this is one of the things we reviewed the other day. So thinking about A is a sequence, okay? Now example is xn equals to -1 to n over n plus 1. So this is not a converging sequence, because actually on one side, if you take n to be an even integer, then the sequence actually goes to 1. If you take n is odd integers, then the sequence will goes to -1. So there's two endpoints, like two cluster points, 1 and -1. Okay. So that's something you need to understand. So once you have a sequence which is not converging sequence, then the sequence may carry some cluster points. Okay. Then if the sequence, so that's things you should be able to observe. Okay. Now here you can do. Last time we did a little bit more than that. So we're talking about interior points, boundary point, closure, and also there's isolated point. So once you have a set, including sequence like that, you can always determine these things, okay? And so you can go home, review this a little bit more. And also I will indicate the second example is a set. It's a set. The set is actually an open disk and with the center removed. So you can see the white dot. White dot means this point is removed, not belong to this set. Okay? So just this indicated by the inequality. X squared plus y squared is greater than 0 and less than 1. Less than 1 meaning that the boundary is not included. And also attached, this set is attached to an outside point that's 2, 0. Okay? So for this set is given. So again, you can ask the question, the interior points and the boundary points, closure, cluster points, and isolated points. So this picture is easier than the previous one. You can see first you have to understand what is interior point. Interior point, that means not only the point itself, including in A, but also the small balls surrounding this point. The entire ball is also included. So you can see that any point which is inside this open ball, not including the center, okay? Anything included this open ball will be the set of interior point. So that's the interior of this set, okay? And the boundary point obviously including the boundaries, right? X squared plus y squared equal 1, also including the outside point 2, 0, and also including 0, 0, that's the center. Even though the center is not in the set, but however, this point itself is a boundary point. Now, it's easier to determine the closure because suppose you can correctly find out what is the interior and also the boundary. Then you add union the interior and the boundary, and this gives you the closure. Okay, so the closure is just the disk itself. Now it's a closed disk itself, including the outside point. And the cluster point. Now, one simple way to determine the cluster point is that the cluster point is everything excluding the isolated point. Okay, excluding the isolated point. So we have only one isolated point, okay? And so you take the closure, okay, throw away the isolated point, and that will be the set of all the cluster points. Okay, so that's once you should review all these concepts will help you to prepare for the quiz. Okay. Now the next one is important. So here we're giving a sequence K. Okay, K equals to 1 over n. It's a very simple sequence, including the limits. The limits is equal to 0. So the sequence plus the limits together, union together, you form the set K, called K. And what we want to show is this K is compact. It's a compact set, Okay. Here, this proof is using the definition of compact set. And suppose you have a covering, open covering for this set. You want to show that this open covering must carry a finite covering, right? So the argument goes like this. Now, since every point will be covered by some open set in the family, so therefore, the limit point itself, that's the 0 point, should be covered by some intervals, okay, by some interval. Here, I'm drawing a ball. It's supposed to be an interval. So this means that since the sequence go towards this limit, so therefore, when n large enough, then all the points will be inside this interval. And then outside of this interval, there's only a finite number of points. Okay, and those outside points, obviously, because they only have finite number of them, which can be covered, each one of them can be covered by just one open set in the family. So totally, they can be covered by a finite number covering, including the first one. So this means that the whole thing can be covered by a finite number open set in the family. So therefore, there is finite subcovering. So this is how you prove this result. Okay, or you can use the Hahn-Boyer theorem. Hahn-Boyer theorem require you to prove that this set is a bounded set and it's a closed set. Now it is easy to see this is a bounded set, right? See, it is bounded, but it takes a little bit more argument to show that it is a closed. Okay, so in this case, actually using the definition of the compact set, it's easier to prove this result. And I want you also pay attention to another result. Now, instead of thinking about this K set, now I'm thinking about an A set. A set is actually the sequence in the previous example. Okay, -1n, then n over n plus 1. So this sequence is not converging sequence, but however, it carries two limit points, 1 and -1. Okay, so actually you can also show that this set is compact using the definition. Now, how do you see this? Actually, this follows exactly the same argument because, again, I draw a picture. Now, this time I have two cluster points, okay, are both denoted by red color. So therefore, these two cluster points, first you pick up finite covering. And so these two red points can be covered by two open set in the family, okay? Then you can see as n large enough, so you can see that most of the point will be goes into these two intervals. Then outside of these two intervals, there's only finite number of set, which can be covered by finite number open set. So with the same argument, you can show that A is compact. Okay, so this is again, it's a very important result. You have to practice writing out how to prove it. Okay. All right, there's other problems so we talked about before, and K is a compact set, and so here is a K is a compact set in R in a one-dimensional space, but also the K can be viewed as a set in the R2 space. Okay, so we're going to show that if K is compact in R, then K is also compact in R2. Okay, so that's the result, and actually I show this detail so you review by yourself. But also you can think about the other way. You can think about the if K is compact. Suppose now you have two-dimensional set K, okay, and which is compact in R2, and then you can look at the restriction of K on the real axis. The restriction should also be compact. So this means that this result is kind of a two-way result. Okay, compact in R implies the compact in R2. Then if you have a compact in R2, then the restriction will be compact in R. Okay, think about this by yourself. Okay, so this is the proof of this result. Basically, you can, very easier, you can use the Hahn-Boyer theorem, because compact means bounded and closed. So in this case, K is compact in R1, so this means that K is bounded in R1. Then I will try to show that K is bounded also in R2. And since K is closed in R1, then we're trying to show that K is closed in R2. Okay, and so this means that the boundedness is an easy part. So for the closedness, you have to argue the exterior points argument. Okay, now suppose you have a point which is away from the set and as a subset in R2. So this point has to be either on the axis away from this K set, right? Or in the away from the x-axis. In both cases, you can see that you can separate them by small wall from the set K. Okay, so therefore it is very simple to show that it is closed. Okay, all right, so this is basically the review. So any questions? Okay, no question. I'm going to now continue with today's lecture, okay? Okay, see. Okay, now let's continue to talk about the uniform continuity. Okay, and the last time we talked about, I'll give you two examples. Okay, and two homework problem. And the homework problem 7 is optional. Don't worry about it. If you want to study by yourself, or I can, if I have extra time, I can talk about this in the other, maybe in the other days. Okay. For number 6, this is a very simple problem, but it is a very important. So it's meaning that if f satisfies this inequality, like fx1 minus fx2 is less than m is a constant, times x1 minus x2, then this will imply that the function is uniformly continuous in R. Okay, now because you can see that the difference of the x actually control the difference of the function value. So that's the main reason why the function is continuous. It's always a continuous function. Okay. So the proof is here. It's very simple. So you can study by yourself. And there's a name for this kind. This is can be considered as a strong continuity. It's called Lipschitz continuity. Okay. Now there's another kind of weaker continuity. Maybe I can introduce later. Okay. So this regarding the homework problem. Okay. Okay. So today I'm going to begin to talk about. Now, last time we proved a very important result. It's called uniform continuity theorem. It says that if a function is continuous on a compact set, the function then has to be uniformly continuous on the same set. Okay, so the continuity on compact set usually give you a very nice result. Okay, so function continuity of the function, assuming function is continued on K, is just assuming function is continued at every point. Okay, on K. It's just a local properties. And then the previous result says that actually the function will be uniform continuity, uniform continuous. So this gives us a global result. Okay, now here, 415 give you another global result. It's called a maximum and minimum value theorem. Okay, this is another theorem regarding function, regarding a continuous function on a compact set. Okay, so it says like this. Now suppose you have a f. It's a function from df to, it's a df defined in the p-dimensional Euclidean space. Now df itself may not be compact, but suppose I have a subset from df, from its domain, which is compact. Okay, let's say that f is continuous on K. Okay, now last time we showed that then this will imply that f is uniformly continuous on K. Now today we're going to show you some additional result. So then the new result is that there must be point x up star and x bottom star, lower star in K. So what does it mean here? There must be a two special point in K such that at these 2 points, f actually achieves its maximal, the f and at the lower star actually achieves the minimum. Okay, so here we cannot at the very beginning say maximum minimum because I don't know whether maximum or minimum will achieve at a certain point. So that's why I write fx up star equals sup of f. The f lower star equals the inf of f. Okay, so in the general case, even though the function, a bounded function may achieve, for any bounded function, you can see that the function always achieves supremum and infimum. But these two values may not be realized or achieved at a certain point of the domain. Okay, I'll show you an example. Think about K equal to an open set, open interval 0 to 1. And the function is just equal to x itself. Now for this function, you can see that what is supremum of this function? The supremum of this function is just equal to 1. Okay, supremum is a limit. Okay, it's equal to 1. Okay, but however, and infimum equal to 0, right? So 1 and 0 is defined by the function value, behavior of the function. But these 1 and 0 will never be achieved at any point within 0 to 1. Within 0 to 1. Okay, so the reason because this K is not a compact set. It's not a compact set, okay? So the problem here, the theorem we're going to show that as long as K is a compact set, then you can always achieve maximum and minimum for a continuous function. Okay. Now, compact set means a set is bounded and it is closed. It's called a compact set by the Hahn-Boyer theorem. Okay. Now, so today we are one of the important things we're trying to prove this. So I'm only going to just prove the X star, up star. I mean, I'm going to show that F will achieve its maximum somewhere. And the same argument can be used to show that F actually also achieves minimum at another point. Okay, so let's now show how we can prove the existence of F star. Okay, so by the definition of the supremum, okay, it means that there exists a sequence of points xn in K, such that the limit of fxn equal to its supremum. Okay, so now the problem is reduced to show that how we can find the existence of a point which takes the limiting value of the sequence. All right, so we're going to see how we can do that. So this is what we have so far, okay? I know that there's a sequence xn, and the function of this sequence goes to the maximum, okay? Now, here we use we use the case compact. Now, it is compact, so therefore it is bounded closed by Hahn-Boyer theorem, okay? So I'm going to use both conditions, case bounded and closed for different purposes, okay? Now, first you think about that case bounded set. Now, for any bounded set, I have a theorem called BW theorem before, right? So for any bounded set, I can always apply this BW theorem. Now, so this BW theorem saying that since K is bounded, so therefore any sequence will become bounded. So therefore there must be, for the sequence, there must be a converging subsequence, X and K. Okay, so this is followed from the fact that K is bounded. I haven't used the fact that K is closed yet. So since X and K is a converging subsequence, so therefore I can define the limit X and K equals to a special point. So that's actually the point X upper star. Now we're going to use second condition. Second condition, I mean K is also closed. So since K is closed, so I know that since X and K goes to X star, so the limit point must belongs to K itself. So this Xn star cannot be exterior point because there are some interior point approaching this. So at most it's in the boundary, on the boundary. Okay. So using the fact that K is closed, so we can see that X upper star is in K. Now we use the fact that F is continuous on K. Now I have a point in K, right? And the function continues, so this being function continue at this X upper star. So the limit of F on the subsequence equals to the function value at this point. That's followed from the definition of continuity, okay? Okay, now what is limit of that? On the other hand, we clearly have that the limit of F and K and K. So that's followed from the F and K, right? Okay, the limit of F and X, the limit of F Xn equal to supremum. So therefore, for the subsequence, the limit F X and K also goes to the supremum, right? There's no difference. Okay, now you compare this inequality or this equality to the previous one. Then you can say the Fx star must equals to the supremum of Fx. That's how we prove the existence of a point at which the function achieves maximum. The same argument works for the minimum. Okay, so for a compact set, if you have a function to be continued on that, and you can say the maximum and the minimum points. Otherwise, the point achieving maximum, point achieving minimum may not exist. Okay. So this complete the proof. There's a corollary, it's a consequence. This consequence says that actually, it's not really a consequence. I mean, it's a slightly different situation. The condition is the same, assuming f is a function defined on a compact set. Okay. Now, if f is continuous on K, then again, there is point upper star, lower star in K such that this time the maximum and minimum is in the norm of f. Okay, the same argument, I mean, applied. If you apply the same argument, you will obviously get this. Okay, so this is not a big deal. But anyway, so as exercise, you can try to write this proof in this content. Okay, now let's move on to the last section of this chapter. So today I'm going to finish this chapter 4. So Monday we're going to have tests, and then next Thursday I'm going to begin. I use maybe three lecture to finish the chapter 5, the last chapter. Last chapter is a short chapter. Okay, now we talk about 4D. It's called the sequence of continuous function. Now, previously when we talk about continuous, we talk about individual function, right? Continuous for individual function. Now here, we're dealing with a different question. We're dealing with a sequence of function in which every individual function inside the sequence are continuous function, okay? So let's see what's the issue here. So let's say that I have a Fn is a sequence. Now this is not a point, sequence of points, that's a sequence of functions. They're all defined on the same domain D. So this function is a vector function from D to RQ, okay? So then let's assume that for every x in D, okay, the limit exists. I mean, limit Fn x exists. Well, in general case, the limit may not exist, but here I'm assuming, okay, for every x in D, the limit exists. Okay, so therefore, you can talk about the limit function. I can define fx to be equal to the limit of Fnx. Okay, so that's the definition. So I have a sequence of continuous, we haven't talked about continuity yet. I have a sequence of functions, these functions are all continuous at every point in D. So therefore, I have a function fx is well defined. Now let's suppose that Fn, for each n, the Fn is a continuous function on D. Now here, I didn't say anything about the D. D is compact or not compact. So when I say Fn is a continuous function on D, that's it. You cannot argue for anything more, whether the function is uniform or not uniform. That's not in our question. Here, I just have a general set, okay? Fn, for each n, Fn is a continuous function. That's it. Now, the central question in this section is whether the limit, this will imply that the limit function f is also continuous. So this is very reasonable. I have a sequence of continuous functions. They're all converging to a function fx. Obviously, I will say that it's desirable to see that fx is also continuous. That will be very nice, right? However, it is not the case. The answer to the above question is no. Now let's consider example. Let's consider Fnx equal to xn, which is defined on 0 to 1. It's a closed set. Okay, so you can see there's a function Fnx, okay, and equal to xn. Now what is limit? Whether the function always converge at every point from 0 to 1? It is, because you can see from this picture. So when n equal 1 is just straight line, then the n equal to 2, that's parabola, and then n equal 3 is a cubic function. Then on. As n goes higher and higher, the function will always confine in this triangle, inside this triangle, getting narrow, and closer to both axes. Okay, so this is so what is limit function? You can think about it. What is limit function? So for instance, suppose you think about, now one thing is clear, when x equals 0, okay, then no matter what n is, the function value equals 0. So all the curve, okay, in this picture, they are starting from 0, starting from image, okay? And other endpoint is clear. So when x equal 1, so 1 to any power is still equal 1. So this means for every n, the fn1 is always equal 1. So that's why all these curves are end up with the same point. That's 1, 1 point. Okay? And now between 0 and 1, something funny happens. So between 0 and 1, this means that x is less than 1. So if you have a number smaller than 1, then you take power getting high enough. As power goes to infinity, then the xn will end up going to the 0. Okay? So this means that the limiting function behaves strangely. So when x between 0 and 1 not equal 1, the limiting function is a constant function. It's all equal to 0. Okay? But when x equal 1, the limiting function happens to be 1. There's sudden jump. So you can see in this example, the fx as a limiting function is not a continuous function because there's a jump. It's not a continuous function, even though every function in the sequence xn is continuous. So this shows that even though I have a sequence of continuous function, then the limit function may not be continuous unless there's some additional condition to guarantee the continuity of f. So that condition is something we want to talk about. Okay, so that condition is also involved the words called a uniform, but that uniform is different from the uniform we studied in the previous section about the uniform continuous. There are two different kind of uniform. Okay, so here we are going to talk about the second uniform. It's called a uniform convergence. So it's been convergence is called uniform. Okay, so let's go back to our situation. Fn, sequence of functions from D to Rq, okay, which converge to f on D. So uniform converging is saying that the function is not only converged to something, but also the function, that convergence actually is subject to some uniform restriction. So that's why it's called uniform convergence. Now, what does it mean? Okay, so we define. We say Fn converges uniformly to f if for every epsilon greater than 0, there is a natural number k epsilon, such that for any n greater than k, and for all x in D, this difference is less than epsilon. Now you need to think about this for a moment. Okay, so this, if you look at that, this epsilon k argument. So what's the difference? Now, suppose we say the function fn converging to fx at some single point x, okay? Then you stay the same thing, right? Except the red part. We're not dealing with all x. Now, the most important ingredient here is the k epsilon. You see, so this k depends on epsilon, that's one thing. But also the k actually should also depends on x, because at different x, the converging rate may be different. Even though we're dealing with the same epsilon, maybe we require different point, may require a larger k, okay? So, but however, here we say it's uniform convergence. This means that no matter which x you're thinking about, you can use the same k epsilon without dealing with any location of k. Okay, so this k works for any locations. So that's why the red part saying that when n greater than k, for all x in D, you will have that. Now, if it is satisfied in this case, by this definition, then the function is called uniform convergence. Okay, and uniform convergence is the right condition for us to guarantee the continuity of f from the continuous function. So here is a theorem. Okay, now here, before we state the theorem, we have to talk about the opposite of uniform convergence. Now, what I mean by opposite of that? That's you logically can negate the previous definition, right? Now, if you negate the previous definition, then you can see that you are going to have the negation of that. Okay, so let's say Fn is a sequence of points which converging to F on D. Then you can see the converging is not uniform. It's not uniform. Okay, now the sequence may still converge to F. There's no problem. But the converging is not uniformly. If only if there is, I mean, you just negate the previous definition. There exists epsilon not greater than 0, such that there exists sequence Fnk and a sequence of point Nk, such that the difference on this sequence of point is always on the subsequent is always greater than equal to epsilon naught. Okay, so this may be an exercise for you to think about the negation of the logic statements. Okay, so that negation. So what does it mean is that no matter how close the point is, okay, the function value may always greater than certain value. I mean, if you look at the previous picture, you can see this function, this conversion is not uniformly. You can see, when the point is close to 1, when x is close to 1, okay, no matter how close it is, you can always show that the value of the function can be greater than certain value. Okay, it's not uniform. Okay, so the main thing now is going to show that the uniform continuity theorem. It's going to say that the uniform convergence is imply the continuity. So let's say that the Fn is a sequence of functions, okay, converging uniformly to F. Okay, sorry, I forgot the words continuous function. So this sequence is a continuous function, okay, uniformly converging to F. Then we're going to show that F is also continuous on D. Okay. Now the proof is not long, but however, it's technical. So you have to learn the argument carefully. So what we need to show that F is continuous. Okay, actually you can see that once I show that, okay, there's another thing. Okay, we're going to show that F is continuous. So the continuity is a local property. So I'm going to show that F is continuous at every point in D. So let's say I pick a point in D, A, called point A, okay? Now, since F is continuous, F is converging uniformly to F, okay? So there exists, so for n large enough, based on our definition, okay, the Fn x minus Fx can be less than any given number uniformly. That means this inequality should hold for every x, for all x, okay? So here I'm technically, I need to choose this less than epsilon divided by 3. Now, since Fn is continuous, so there exists a real number delta epsilon, okay? Sorry, it's k epsilon, I'll keep, no. Okay, don't look, it's a delta epsilon. Now we're dealing with continuity, okay? So there is a real number delta epsilon, okay? Such that for all x in D, so here's a local property, okay? We're not dealing with the local property, the uniform continuity. It's just the continuity. So when x is sufficiently close to A, which is less than delta epsilon, then the Fn x minus Fn A is less than epsilon divided by 3. So what I'm doing here is, first I choose n large enough to make first inequality hold. Then I fix this n. And for this fixed n, the Fn is continuous. Then I use the continuity property to show that when x is close to A enough, then for this Fn, special Fn, the value between the Fnx and Fna is also less than epsilon divided by 3. Okay, so that's the basic setting. And then we go to the trying to show the result. Now for all x in D with this inequality, okay, that means letting x is close to A within the delta distance, then we're going to have, then I'm going to look at look at the limiting function. So we're going to show that fx minus fa is less than epsilon. Okay, then this shows that the limiting function f is continuous at a, right? Now look at this difference, fx minus fa. I'm going to insert 4 terms into this expression. Okay, so I'm going to insert minus fnx plus fnx minus fna plus fna. So that's the technical part. So these terms are canceled to each other. So it's not going to change the entire value. And then I use the triangle inequality. So you can estimate by these 3 difference. Okay, and then you compare it to the previous the arrangement. Now the first one, and the first one, you see there's 3 terms on the after this inequality. The first term is less than epsilon divided by 3. The second term is using the second inequality. The third term goes back to the first inequality. So what I'm saying here is that the because of the uniform continuity, okay, the first inequality are established here to handle the first and the third term. And the second preparation give us to handle the middle term because they are all less than epsilon divided by 3. So total is epsilon. So this shows that the function is actually continuous at A. So that's a proof. It's called a uniform, the preservation of the continuity. Okay. All right. Any questions? So that's the material I'm going to cover, and there's some additional Dini theorem after that, which I'm not going to because we don't have enough time to cover. Any questions? So there's 2 problems, 8 and 9, and these are all problems related to the uniform continuity and uniform convergence things. Okay, so you can spend time to practice on these 2 problems. And again, after the test next Thursday, I'm going to have something to say about these 2 problems. Now, these 2 exercise problems are very important. Okay, should you pay attention? But right now, I mean, during the weekend, you want to prepare for the quiz. All right. Okay, so that's all I have to say today. Any questions? Okay, so today, so I'm going to I'm going to record it. I mean, today's lecture is recorded. I'm going to do the upload and then the whole, and also the office hour. Okay, all right. Thank you. Bye bye.